Hi, folks. Welcome to the Nobel Prizes of 2023. I'm sure you all do that too. We have a regular over the last 5 years, thanks to our um, missing facilitator, Ken Burns, who's been a close friend of our present speaker and vice versa. And so this is a reminder of how beneficial Ken was in this program. Our speaker is Dan Purich, and he's a biochemist, but he has been able to talk on other prizes than chemistry, on physics, and he has a way of communicating very effectively to us. So we welcome him. He didn't want me to tell you about all his academic positions because they're going to be one of the slides, so I'll pass with that, except to say we're very grateful to have him talk and how he can clarify things that seem totally opaque to me. And that's the reason I started the Nobel Prize courses, so I could find out things without sweating too much. And so welcome, Dan. I want to just, before you speak, just give a little bit of advice to people. We're going to have a partial eclipse of the sun in about an hour. It's going to start. It's going to peak around 3:30 or so. But they tell you don't look directly at the sun because, especially without any protection, because it will burn your retina, and that's true. So there's a trick that I've used over the years. I use a pair of binoculars, and I point the ocular portion at the sun. I'm not the ocular portion, the other portion, the wide end, at the sun, and line it up with a piece of light white paper or cardboard, and you'll get an image of the sun, and you'll be able to see as the moon starts biting. Now, we only get up to about 60% of the part of the eclipse. We don't get the total eclipse. So if you can find a pair of binoculars, even opera glasses, this is a safe way at looking at the new moon. We hardly ever see a new moon, and this time we will. So, Dan, it's all yours.
Okay, good to be here. Actually, the other way to look at the sun is to keep in mind that the shadows under a tree are dappled because the tree acts like a pinhole camera. And so you will see the crescent shape on the ground multiple times because the tree has many little holes through which the light can pass. I'm delighted to be here today. I'm a regular, I suppose, but I'll just take a minute and say that I'm a biochemist, it's true, but I studied chemistry both as a graduate student, and then when you become a professor of chemistry, you really study chemistry because you have to teach it. And so I taught in practically every different chemistry course in the chemistry department at UC Santa Barbara, and I got to love chemistry very much. In fact, I've loved chemistry my whole life. When I was an undergrad, I'll tell you that I saw someone I thought I would like to date, but I knew that she was an economist. And so she asked me what I studied. And I had to think for a minute. I said, I'm a sociologist. That sociologist is close enough to being an economist. And then after the first date, she said, you know, I don't think you're really a sociologist. I said, oh yes, I'm an electron sociologist. And that's what a chemist is. So I was a professor at the University of California, Santa Barbara. Then I came here as chairman, and in no small part because I admired what Ken Burns, who was then leaving, had done in his department. I've been on various editorial boards, and the thing I'm particularly proud of is having discovered the actoclampins These are the force-producing protein complexes that allow all of our cells to crawl. So my background in physical biochemistry paid off because it took a fair amount of physical chemistry to understand what was happening. And I love enzymes. You can see I've written 15 books on enzymes. Now, the reason I'm here today is because of this guy. And Ken Burns and I just automatically took to each other. I say what's special about Ken was he was a virologist, a leader, a family man, and a friend. And when we were here all a month ago, we saw how overwhelming it was, how many people were here. Laura happily had advised me to come early so that I could find a parking spot. Robert Frost wrote a poem that I think is very appropriate for how Ken's modus operandi. It says, when a friend calls to me from the road and shows his horse and slows his horse to a meaning walk, I don't stand still and look around on all the hills I haven't hoed and shout from where I am, what is it? No, not as there is a time to talk. I thrust my hoe in the mellow ground, blade end up and 5 feet tall, and plod. I go to the stone wall for a friendly visit. Ken Burns, as a leader and as an important scientist, was always busy. But if you saw him in the hallway, if you saw him anywhere, he stopped to take the time to talk. And in that experience with him, I forever feel that every time that we met, even though he would deny it, I learned something from him. Occasionally, I learned how not to tell a joke. Other times, I learned how to tell a joke. But it was a great experience. And so I dedicate today's lecture, for better or worse, on my performance. I dedicate it to my dear friend. So today, what our goal is to discuss why these three individuals got the Nobel Prize in Chemistry in 2023. And we'll come to them each, so I won't mention their names here. But these three hail all from the United States, although the last, Yakimov, actually did his training in the Soviet Union. But Wendy, we'll see, has a very interesting background. And Louis Bruce is someone that Ken Burns would have liked because he hailed originally from Cleveland, Ohio. So here is Bowendi. I call this Meet the Laureates. And he is a Tunisian-American French scientist. His parents were Tunisian. They went to France, and he was born there. But somewhere around 11 or 12, he came to the United States. And there he studied at Harvard, and then later at the University of Chicago. And his PhD mentor suggested that he should make contact with Louis Bruce, who was then working at Bell Labs in Murray Hill, New Jersey. And so he did that, and Bruce had a career-changing experience it was for Bowendi. And his hobby is skiing, and from what I read, he especially likes skiing with his daughter because he seems to be a better skier than she is. Louis Bruce is an American chemical physicist. And by the way, chemistry and physics are very closely related. In fact, they're about the properties of matter. We all want to study the properties of matter. And so physicists, we say, do very exact measurements on impure substances, whereas chemists do imprecise measurements on very pure substances. That's the only difference between them. Now, Bruce was born in Cleveland, Ohio, educated at Rice and Columbia, and then he moved immediately to Bell Labs and stayed there for about 25 or so years, and then returned to Columbia, where he's still a professor. And then the third in this group the original discoverer of quantum dots is Alexei Ekimov, and Russian solid-state physicist, born in the USSR, couldn't find his city. Maybe it's top secret. Leningrad State University, and then at the Physical Technical Institute of the Academy of Sciences. And like all Russians, he apparently likes chess. I haven't met a Russian yet who doesn't like chess and who isn't better than me at chess. So today what we're going to be talking about is light. So I have to give you a little bit of a background about light because not all of us know about this. So I want to spend a little bit of time. Now, when we have a lamp on the left at the top there, the lamp, as it's emitting what we think is white light, is actually a composite of all the different colors of light. And we know that because when we take sunlight and pass it through a prism, we see the rainbow of colors. And so what a UV visible spectrometer is a device that takes advantage of the fact that I can take a prism and I can rotate the prism so that the light is passing through it and it's casting out this rainbow. I can adjust so by changing the angle, that I can set the color of light that's going through the sample. And by measuring how much the light intensity is before and after it passes through the sample, I can get a readout on how it's interacting with that material. And it turns out that molecules don't interact with all different colors of light the same way. Instead, it's said that the absorption is quantized. And you shouldn't be worried about this word quantum or quantized, but what it really means is that there's an energy difference between the ground state, where the electrons are, these are the valence electrons, those that are used in making bonds. Those are in a ground state, and then when light is absorbed, we promote these electrons up to an excited state. And there, those thinner lines that are shown in the ground state and the excited state are what are called vibrational energy levels. And so we have a relaxation, they get down to a low-lying excited state, and they emit, and what they emit we call fluorescence. And if a molecule has that certain distance in energy, that distance only corresponds to one color of light. And because each color of light is at a different frequency, frequency has the unit down on the bottom, nu, and so the change in energy is related to that frequency. Now, if we use the spectrophotometer down on the lower part of the slide, we can measure the ability of different molecules to absorb light. And here I show you chlorophyll A, chlorophyll B. I'm a biochemist, so I choose these molecules, and other photosynthetic pigments. And what these molecules on the bottom are doing is that evolution has placed them so that the spectrum of chlorophyll actually, at one point about 1 billion years ago, exactly matched the spectral output of the sun. So the two fit together so well that the chlorophylls together, A and B, they could absorb so much of the light. When they absorb the light and the electrons go to the excited state, those electrons have the energy of that light. And if those electrons can be captured into biomolecules, that's photosynthesis. And that's what allows us to have the energy. We only exist because plants provide us the energy from the sun. So you can now see why the spectrum of each one of these molecules is different. You can see in your mind, because what you know then is that that energy gap between the ground state and the excited state is different. The farther into the red, the smaller the energy difference, because red light is less energetic. The farther to the left, then we have ultraviolet light, and that's the high energy. And on the top here, I show you actually the output of the sun, particularly today, since we're talking about the sun. This is the output of the sun in terms of the visible spectrum, and you can see that that middle part is what's harvested by these various photosynthetic pigments. So that's my little review of how light interacts with matter. And now what I want to, another property that we need to know a little bit about is the difference between a conductor, a semiconductor, and an insulator. An insulator is also called a dielectric. A conductor has free electrons. These electrons move around very, very freely. So if I put electrons into a copper wire, the other electrons are so free that they just can conduct the charge very easily. Semiconductors have weakly bound electrons. That means that there's still an energy difference between the ground state and this excited state. And if we use electricity, or if we even in some cases shine light on them, they can actually now become conductive, but they're not as conductive as a regular conductor. And these include molecules or substances like silicon and germanium. And then the insulators are substances that have very tightly bound electrons. So it takes a lot of energy to be able to break the electron away from the molecule and put it up into the excited state. And dielectrics include things like glass and rubber. And we'll say a little bit about glass in just a minute. The key point, and the reason why I tell you this, is that these quantum dots that we're going to talk about only work because they have a core of semiconductor. And so with that, I want to say who did what in getting this Nobel Prize. And the first work was done about 45 years ago by Alexei Ekimov. And what he discovered was that he had doped glass with a little bit of copper. And when he did this, the copper tended, under the conditions he did it, not to be uniformly distributed through the glass. And in the process of working the glass, he put certain tensions on the glass as it was cooling that the copper ended up confined in certain places. And what he noticed was that these molecules fluoresced. And he noticed that the color of light that came out was related to how large the little area was. That if the area was very small, the amount of light was very blue, and if these little spaces were bigger, the light was red. And he came up with this idea that because the light was confined in a very small space, that had an effect on the energy changes within how light interacted with matter, and he called that quantum confinement. Then, in 1982, Louis Bruss was working with various semiconductor materials, and he had made colloidal solutions of them. A colloidal solution means that you have molecules that have aggregated, and they're fairly big, but they're not so big that they settle out of a solution. Instead, just the thermal motions, whenever we warm something up, there's a lot of thermal motions in water, and that keeps them suspended. And as he was looking at the fluorescent properties of these, he saw that there were these little specks that had color, and that the size of the speck affected the color that he had studied. That was the fluorescence. And then Mungi Bawendi came to his laboratory, and that was a major change in Bawendi's life. He saw this effect, and he realized that if they're related to size, that he should figure out a way to make particles of a certain size. And so he started to do this. Now, people had studied crystallization and how you make molecules aggregate to a certain size. We've all done this at various times in our life. We make a solution of sucrose, of table sugar, and we make it in warm water. Then when we cool it, crystals start to form. And that process, that if we scratch the inside of the glass, which you don't typically do with your favorite glass that's at home, but if you did, crystals would even form more because these little surface tension effects have a big effect on crystallization. And so Bawendi wanted to make crystals nano-sized crystals. And he needed certain properties. He needed a semiconductor because that's what Bruss told him it had to be. And he had to make them so they were very small. And there's a property, there's an equation, a famous equation in physical chemistry called the Gibbs-Thompson equation. And I won't tell you about it, and you'll say, thank you very much. But I will say that that equation predicts that exceedingly hard substances have an easier time to come together and form these little nuclei, these little crystal-forming components. In fact, this was known for a long time. We've all, given our age, we've all read novels or read some of the humorous articles of Kurt Vonnegut. Kurt Vonnegut inspired me to think about science and science fiction when I was a kid. But he had an older brother, Bernard. And Bernard Vonnegut understood crystallization very well. And he understood that one of the hardest crystals was silver iodide. And so what he did was he made a solution of silver nitrate, it's soluble. He made a solution of sodium iodide, it's soluble. He mixed them together, and he could make these tiny, tiny crystals. And he could do it, these crystals, they were so small, they had only 26 to 30 molecules in them, very, very small. And why did he do this? He was a meteorological scientist, and he invented cloud seeding because he could go up in the sky and mix these solutions in the sky, and these little tiny particles that he formed would act like a nuclei for water to condense on, and each raindrop then had a little tiny particle of silver iodide. And the silver iodide, because there's only 26 molecules in one aggregate, it had no effect on the purity of the water that fell to the ground because it was way below parts per billion. It's still the method of choice for cloud seeding. But building on those principles, Bowendi figured out a way to make these out of a molecule known as cadmium selenide. It's a compound made from cadmium, which is a metal, and selenium, which is a lot like sulfur. And this allowed him to make these beautiful quantum dots of a specified size because he could control he could make all these little tiny nuclei and let them grow for defined periods of time, stop them, and then he would coat them. And I'll show you a little bit more about that. And from that, a lot of things have happened over the last 30 years. So here are some of those quantum dots. You see them there, and you see how regular they are. And he was able to make those all from just mixing the reagents under very defined conditions. And these are tiny. They're around 2 to 10 nanometers. And you can see how uniform they are. He is good at making remarkably uniform particles. And you might wonder, what is 2 nanometers? So I wanted to give you an idea how big 2 nanometers was. So 1 nanometer is to the diameter of a volleyball what the diameter of a volleyball is to the diameter of the Earth. So from that, you get an idea that 1 nanometer is pretty damn small. Okay, that's the only, I think that's the best definition, pretty damn small. Now, the reason he wanted to make these uniform in size is that there's an unanticipated property of these molecules that Bruss and had discovered, and that is that the particle size dictates the energy of light that's emitted. So if you make larger ones, they emit red light, and if you make very small ones, they give off blue light. This is very significant because the chemical composition inside is identical. So it has something to do to just the little space that they're occupying. Now here's a quantum dot. I said to you that the interior is made of cadmium selenide, and that's the semiconductor. And then there's a shell put around it that confines it, and if I shine light or put electricity into the system, that shell, that core will be what fluoresces. And then zinc sulfide is used to coat these, and then an organic coating is put on as well. And this organic coating can be a polymer. Usually it has some negative charges on it, so these molecules won't aggregate with each other. They'll stay away from each other by repulsion. And so it's this quantum dot core that has these special properties. And we say that the electrons are down in that valence, that ground state that I showed earlier. If we put light or electricity into them, we promote the electrons up into the semiconductor part where the electrons are free enough to move around. And because the atoms are so close to each other in this, unlike when we have a solution of atoms, something special happens in this very confined environment. And what is so special is that the energy difference between the ground state and the excited state changes depending on the size of these particles. And as a result, the largest particles, as shown on the left at the bottom, are red, and the smallest ones are blue. And so this gives one the ability to using one chemical substance, cadmium selenide, to make different colored particles. This may not seem very important to you, but you'll see why it's important in just a few minutes. In fact, it's wonderfully important. Now, it turns out that these are not only of different color, but they are brilliant in their fluorescence. So they're bright enough that if you're within a dark room, or even a room with this much light, if we turn another 1 or 2 lights off, if you were to excite them, a single nanoparticle you would be able to see. Mind you, it's so small, but yet it's so bright. And that's the key property of these quantum dots. Now, these quantum dots are special because they're miniature crystals. They have a very limited number of electrons compared to the number that we deal with when we're talking about how much food we eat. We're eating 10 to the 20th, 10 to the 25, 10 to the 23 molecules. So here we're down by a great magnitude from the kinds of numbers of molecules we typically deal with. And the sizes are very carefully arranged so that from Bowendi's work, he can make these very uniform different sizes. And these small sizes allow them to have spectral quantum behaviors because the quantum dot is much smaller than the wavelength of light. And that's the key part to all of this. If you take, for example, a quartz fiber, when AT&T wants to bring quartz fibers in to have all of us start using their cable television, then they're using a fiber that's pretty large. But if you pull on that fiber, heat it and pull it, you can make it so thin that it too will have some of these properties if you filled it with a semiconductor. Now, when excited with light or electricity, the electrons move to that higher energy level, and then they start emitting each electron as it comes down. It releases its energy as a photon, and that's the fluorescent light that we see. And that wavelength depends upon multiple things that Bowendi was able to control. He could control the crystal size, he could change the composition, he could even though working with these small particles, he could alter their shape. And all these things changed their properties. So just to say a few words about quantum confinement, I show you one of my favorite slides. It says, when you put it that way, it's really obvious. And I put the Schrödinger equation down in the corner there, okay? But when I'm teaching enzyme kinetics at the medical school, I put the Michaelis-Menten equation for enzyme kinetics down there. And my students give a harumph at that point because they don't want to learn any equations. But so I've converted this slide. I think it was a New Yorker slide, right? Because the noses are characteristic from New Yorker. And Schrödinger was actually a pretty handsome guy. So it can't be Schrödinger there. So people have worked out some aspects of quantum confinement, and they can relate energy changes. They can do all this quantum mechanical studies, although it's not completely known. But what's happening when these particles, the electrons, are restricted to very small spaces, their electric field is affected by their confinement. And this has a big effect on, at the nanoscale, these particles having fixed energy levels that are different. They're very different than when I take a solution of molecules, because that gives a continuous spectrum. These molecules are bumping into each other. They're not fixed in position. And what happens now is that with these quantum dots, because they're so brilliant, it turns out that they've had big effects. They can be used in quantum computing, in solar cells, in televisions, and it's quite remarkable. So this is a Nobel Prize that has tremendous practical implications. And we can make solar cells out of them, biosensors. I'll make a comment about that in a minute. You can develop ways to deliver drugs. You can do optical sensing for detecting things at very low levels. You can even have them act like catalysts for carrying out certain reactions, because electrons are used in chemical reactions. And one of the broadest uses is, if you bought a TV recently from Samsung, you bought a QLED TV. Samsung owns the market, has cornered the market on quantum dots. So if you want a TV that is going to, most of us, when we bought a TV when we were younger, we kept it for many, many years. Now, when you buy an LED TV, after about 5 to 7 years, the fluorescent molecules get degraded, and you'll see a dimmer and dimmer picture. You think it's you, but it's really the TV. Yes, we're all getting dimmer, but the TV is getting dimmer faster than we are, okay? And in fact, to slow down that dimming, what organic chemists have done is replaced all the hydrogen atoms in these fluorescent molecules with deuterium atoms. Deuterium is a heavy isotope of hydrogen. And the net effect is that when I wanted to buy deuterium for doing experiments with enzymes, I could buy it cheaply. Now the price of deuterium is 150 times higher than it was only 10 or 12 years ago. That's all to slow down the degradation of your LED television. But these quantum dots are cadmium selenide. They have no hydrogens, they can't get oxidized, they're very, very stable. You can shine light on them practically forever, and they will always be brilliant. So Samsung has taken advantage of that. And they have created the QLED TV. And quantum dots, because they're so bright, we say they have a high luminance. And this brightness is very key to the performance of a television. It increases the contrast ratio. And the second thing is that because you have such good control over color, and you can make color of many different wavelengths, you can even get more brilliant colors. It can be a more natural color. Third, it turns out it increases the sharpness because these particles are so small. And so instead of having an LED that's much, much larger, you make these quantum dots, and they give you a bright light. Remember I said in a dim room, you can see a single one of these, so you can just imagine how bright they are. And then against the background, for example, back here, we have a black background. What happens is because the dot is so small, when it's not on, you see mostly black. And so the blackness of the TV, the dynamic range that you're looking of your TV is there. But most of all, QLED displays are 1,000 times more stable than organic molecules that have been made into LEDs. And so this has turned out to be a major advantage, and Samsung rules the roost in this. Now, because I hail from a medical school, I will tell you a little bit about quantum dots being used in biosensors. And I'm only giving you 2 examples today, but there are, I looked up, there are 7,000 or 8,000 patents in the last 5 years that are using quantum dots in one way or another. So quantum dots are affecting our lives, whether we know it or not. And they can be used as biosensors. And a biosensor is some device or technique that uses biological molecules, usually enzymes and antibodies, that allow us to detect specific chemicals. And an example of that is we might want to find out a cancer cell might be expressing different proteins on its surface than the normal cell. And pathologists have figured this out for many years. They've used fluorescent antibodies to detect these differences. And so someone like Ken Rand, even though he's a virologist, he would be able to even figure out what's happening. My wife is a cytopathologist. She sort of looks down her long nasal bridge at people like Ken, who are more clinical pathologists than anatomical pathologists. And I suppose that the opposite is true in that department. But in any case, the biosensor takes advantage of these antibodies and takes advantage of quantum dots. So here's a diagram. I want you to first start in the upper left, and you see one of these quantum dots, and it has that organic coding. And why is that organic coding so important? Turns out that cadmium selenide causes cancer. So you don't want it around for very long. You want it so that you could quiz and do something with it, but you want it to flush out of the body, and you want to put a coating on it so that none of the molecules come out. And then on the right, I show you that there are some cancer-specific antibodies, a certain fragment called an FAB, and a fragment that's the fragment that binds to the antigen, the specific protein that it recognizes. And we can have a number of these, and they're attached by these blue molecules, or depicting the blue molecules, that's polyethylene glycol. It's a polymer to which we can attach things. And in the center is a liposome. A liposome is made by mixing fatty acids with water, and the fatty acids will come together. Their long non-polar units will form a bilayer. And this bilayer is the same kind of bilayer that's in every one of our cells. And within this liposome, you can load this with an anti-cancer drug. You can load it with enzymes and various other things to deliver to a site. Now, what's special about quantum dots? Now, people have been doing this with other fluorescent molecules, but other fluorescent molecules, you'll have to attach many, many fluorescent molecules to that liposome because they're not so bright. So by having these molecules that are so very bright, they act like a beacon. And so now what you can do, for example, is take these quantum dots and you can target them for studying and identifying and localizing tumors. For example, these are 3 nude mice that have had a tumor implanted in them. And then using the detection system I've just shown, if you put them in the dark, these quantum dots are so bright, you can see right through the skin, you can see the color, which is quite remarkable. And on the right, you can see the quantum dots shown as they're brightly attached to these cells. Now, why is this so important? Well, if my friend Bill Friedman were here, he's a neurosurgeon, he would tell you that the big problem for a neurosurgeon is that they're, unlike if you're doing a tumor in a liver, you could take the whole lobe of the liver and safely isolate the tumor away from the body. But when you're going into the brain, it's called marginless surgery. There are no margins because whatever you take extra causes a deficit for the patient. So what's being done is because these quantum dots are so brilliant, what you can do is you can open the brain. This is all being done just experimentally right now, but you can then take antibodies attached to the quantum dots. You can identify, say, where a glioblastoma is, and you would see it in the operating room, and the surgeon can just remove all the bright dots. And he can go after, or she can go after much more of the cancer. And even though it's marginless, you're getting the cancer-causing cells. Because the problem with something like glioblastoma is that you might get 80% of it and give someone another year to live or 8 months to live, but it's hard to get all of it. What you want is 100% out, but you don't want to damage the brain. So these, by being so bright, what surgeons can do is they can have a device that they can electrocauterize regions of the brain, and they can have at the tip the bright light shining, and wherever they see the quantum dots, that's where the cancer is. So it's a brilliant technique. So with that, if I can press one more, I will say that that brings me to the end of my description, and I'd be happy to answer any questions.
Tremendous. I have a question first, if nobody else has one. So it's highly luminescent. It's really brilliant, which means there's a great deal of energy released. So
A great deal of energy to do what?
to produce the light.
Not so much. I mean, you shine light in,
Right.
and the light that you shine in is typically bluer than the light that's coming out
Right,
in most
right.
fluorescents.
So
Because the electrons are in a semiconductor band, you can end up with 2 of these electrons in one cadmium molecule, and one energizes the other, and it's believed that causes this light to become bluer.
so
Usually the light that you put in is bluer than the light by fluorescence that you get out, but now you can
Because
change that.
So if I use a word like efficient, well, you just have to accommodate for all the energy in and out.
Yeah, and you're not getting more energy out.
No, okay.
It's
Yeah.
just that you're using several photons to put
Mhm.
energy in, and then the one photon that's coming out is a brighter photon.
I see.
It's a bluer photon.
Right, right. Questions? Another nanotechnology. We have a center on campus of nanotechnology.
Right, right.
I always expected that.
And nanoscience is big at UF. People are trying to figure out how to use particles in different ways. I had a grant that was a nanoscience grant from the DARPA, which is the Defense Advanced Research Projects Agency, a long name. And DARPA wanted to develop some of the cell motility experiments that we knew how to do. For example, we could make microtubules, which are long polymers, and we could attach them to motors, and they could spin, and they could stir a solution. Now, you might wonder why you'd want to do that, but what DARPA was figuring out was that you could make little bio devices that were so small that could detect dangerous molecules, and they could glue them onto the backs of ants or on the backs of various flying insects. They could dump the flying insects into an area and know whether it's safe to go into that area, because they could look from above, and these highly fluorescent molecules would then say, there's a bad thing down there. There's a bad substance. So there's a lot of different nanotechnology being done at UF.
Yeah, I've been concerned about making drones the size of mosquitoes.
Right, you can do all sorts of things where you use the drone to deliver these kinds
Mhm.
of molecules.
Yeah.
And so I've always thought, by the way, that since enzymes are in the nanometer scale, that I've been a nanoscientist for a very long time. Although people have said, don't be too proud of that. That just means I'm a very small scientist.
I see.
Okay, and you want to be a large scientist.
I
and
see,
you're
a
big.
nanosociologist.
So, yeah,
A
but I think Ken had a
nanosociologist.
question.
Oh,
Did you,
good.
Ken? No? Okay.
Well,
Yes. So you mentioned in the TVs that where a quantum dot doesn't emit any light, it's black. And is that a problem for screens? And do
But what
they
it
have to
means is,
compensate?
what you want is as black a screen as possible when you're unilluminated, so that you have dynamically the darkest screen. So when you have a regular LED and it's larger, then the light in the room reflects from it, and you get more light and less blackness at that point. So if you go and you look at a Samsung TV, they're utterly brilliant. They're quite amazing, and this technology is making them billions of dollars. The other advantage, because these particles are so small, you can use just a regular printer, and you can print the screen. So you put the dots where you want them, each one of different colors where you want them, using not a 3D printer, just a regular printer, a high-resolution printer. And so you have this screen with all the electrical leads on the surface, and now you just spray them or print them so that you put them at the right positions. And now you don't use light to illuminate them, you electrify them, and that frees the electrons. They get to the excited state, and then they fluoresce, and you get the color out of the TV. So they're pretty amazing. And I mistakenly bought an LG TV a few years ago, and I'm ready to buy a different TV, although my Sony TV many years ago I had for more than 20 years. So our ways have changed. We're more disposable now than we think about things as being so disposable.
I have a question and a comment, so I'll do the comment first. Once again, you made an engineer think he understands what you've been talking about. And the question is, when you turn on these Q dots on your TV so that you can see the picture, do they continually fluoresce as long as they are electrified?
They are, that's right.
Okay.
They're short. Whereas now people have developed phosphorescent quantum dots, and now they stay bright for 5 or 10 seconds after you turn off the electricity. And that's because the transition from the excited state back to the ground state, it goes through another little step. Instead of being what we call a singlet state, it moves over to something that physicists would know is called the triplet state. And then from that, it comes down slowly. So yes, fluorescence is a prompt emission of light. It emits super fast. In fact, most fluorescence is occurring on the picosecond to nanosecond time scale. So it's very fast. And as long as you have a sharp switch for the electricity turning on and turning off, so that it comes up and then goes off, then the light will come off, up and off. So it's pretty cool.
Thank you.
Yeah, you're welcome.
so is this not a conspiracy of obsolescence? No?
Well, it's just that, when you see something better, you want it. That's why I have a Mercedes SL550, as it was much faster than any other car I ever had. And the only time I went faster in my life was on the ground was when Buck Ruffin, I don't know if any of you knew Buck Ruffin, but he was a faculty member at UF, very interesting guy. And he took me one time to Cedar Key at 130 miles an hour. And when I said, Buck, what's going to happen when we get a ticket? He said, oh, I've already called the police and they know we're coming through. He was a very well-positioned guy, and he could he could move at those speeds, yeah.
So I want to ask if Dr. Freeman, using the technique you described to colorize and thereby identify ganglioblastomas, that he was implying that these were actually or theoretically completely removable.
Well, you don't know. You don't know. But what happens is that some surgical techniques that people are developing, remember I said you have this liposome, and what you can do is make it so that the liposome is sensitive to certain molecules that are on the surface of certain cells. There are lipases that are even near certain cells. So they break the liposome. The liposome releases an enzyme. There are enzymes that break the bonds between cells. There are molecules called elastases, others that do these kinds of things. Even trypsin, the digestive enzyme, can do that. So now you could open the spaces between the cells so these can penetrate, and you can see even, you get a better sampling of where the cancer cells could be. So you can do things more after you've delivered them than they can act locally. So there are a lot of cool things. When I got this assignment from Ken to give this talk, and it was an assignment, and Laura understands that better than anyone in the room. When Ken assigns the tasks to somebody, it will be done, okay? And when I did this, I started to read more and more about quantum dots. Of course, I had read about them before, but then I came to appreciate what a revolution they are, because signaling in all sorts of ways is better off when you have bright light sources, and they're made so cheaply. These quantum dots are dirt cheap, and so they're quite remarkable.
It's good you did your homework very
Well-
well. Thank you very much. If there's no further questions, there's a eclipse, partial eclipse coming, and
Right.
so enjoy it. Thank you so much.
You're very
Really
welcome.
interesting.
Thank you.